Mechanical Engineering Handbook for Electrical Technology and Machinery. Written by Phil Gilbert. Narrated by Kevin Brooker. Part 1. Fundamentals of Mechanical Technology. 1. Introduction to Mechanical Technology. Mechanical technology encompasses a broad spectrum of techniques and tools used in the design, analysis, manufacturing, and maintenance of mechanical systems. This field merges principles from physics, engineering, and materials science to create and improve machinery and devices that perform specific functions. Historical development. The evolution of mechanical technology is a testament to human ingenuity, marked by significant innovators that have transformed societies and industries. In ancient times, early humans utilized basic tools such as levers, wedges, and inclined planes to aid in tasks. The invention of the wheel around 3500 BCE revolutionized transport and labor. Ancient civilizations also harnessed the power of water wheels and windmills to provide mechanical power for grinding grain and pumping water. During classical antiquity, the Greeks and Romans made significant contributions to mechanical technology. Engineers like Archimedes and Hero of Alexandria developed the screw pump and early steam-powered devices. The Romans advanced road construction and aqueduct systems, applying mechanical principles to infrastructure. The Middle Ages saw the refinement of mechanical clocks, the development of trebuchets for warfare, and the increased use of water and wind power in mills and workshops. In the Renaissance, figures such as Leonardo da Vinci showcased advanced mechanical concepts through sketches and designs, including early versions of helicopters and tanks. The invention of the printing press by Johannes Gutenberg in the mid-15th century revolutionized information dissemination through mechanical means. The Industrial Revolution in the 18th and 19th centuries marked a pivotal moment in the history of mechanical technology. The development of the steam engine by James Watt and others led to the mechanization of factories and the birth of the modern industrial era. Innovations in textile machinery, such as the spinning jenny, power loom, and the cotton gin, transformed the textile industry. The creation of steam-powered locomotives and ships facilitated faster and more reliable transportation of goods and people. The 20th century saw the rise of the automotive industry, with Henry Ford's implementation of assembly line production revolutionizing manufacturing and making automobiles affordable and accessible. The Wright brothers' successful flight in 1903 ushered in the age of aviation, leading to rapid advancements in aircraft technology. Both world wars accelerated technological advancements, resulting in the development of tanks, aircraft, and other military machinery. In the late 20th century to the present day, computer-aided design, or CAD, has allowed for more precise and efficient development of mechanical systems. Robotics and automation have revolutionized manufacturing, increasing efficiency and reducing labor costs. Innovations in materials science, including the development of composites and nanomaterials, have expanded the possibilities for mechanical technology, enabling stronger, lighter, and more durable products. Looking towards the future, artificial intelligence, or AI, and machine learning are being integrated into mechanical systems, leading to smarter and more adaptive technologies. There's also a growing focus on sustainability, driving the development of energy-efficient machinery and renewable energy systems. Additionally, 3D printing is transforming production processes, allowing for rapid prototyping and custom manufacturing. The field of mechanical technology continues to evolve, driven by human creativity and the relentless pursuit of efficiency and innovation. Each historical milestone builds upon previous knowledge, propelling the field towards new and exciting advancements. Applications in modern industry. Mechanical technology plays a crucial role in various sectors of modern industry, driving efficiency, innovation, and productivity. Below are some key applications of mechanical technology across different industries. Manufacturing. In manufacturing, mechanical technology is fundamental to the production process. Advanced machinery and equipment, such as CNC or computer numerical control machines, enable precise and efficient manufacturing of complex parts. Automation and robotics have transformed assembly lines, allowing for faster production rates and reduced labor costs. Additive manufacturing, or 3D printing, is also gaining traction, providing the ability to create custom parts and prototypes quickly and cost-effectively. Automotive. The automotive industry heavily relies on mechanical technology for the design, production, and maintenance of vehicles. Advanced manufacturing techniques, such as automated welding and assembly, ensure high quality and consistent vehicle production. Mechanical technology also plays a role in the development of new materials and components, such as lightweight composites and high-performance engines, which improve fuel efficiency and performance. Additionally, innovations in robotics and automation streamline the assembly process and enhance safety. Aerospace. In the aerospace industry, mechanical technology is essential for the design and manufacturing of aircraft and spacecraft. Advanced materials such as carbon fiber composites are used to create lightweight yet strong components. Precision machining and fabrication techniques ensure the reliability and performance of critical parts. Mechanical technology also supports the development of propulsion systems, aerodynamics, and structural integrity, enabling the production of safe and efficient aircraft and spacecraft. Energy. The energy sector benefits significantly from mechanical technology in the exploration, production, and distribution of energy resources. In the oil and gas industry, mechanical technology is used in drilling equipment, pumps, and pipelines to extract and transport resources efficiently. Renewable energy technologies, such as wind turbines and solar panels, also rely on mechanical systems for their construction and operation. Mechanical technology plays a role in the development of energy storage solutions, such as batteries and flywheels, which are essential for maintaining a stable energy supply. Healthcare. Mechanical technology is crucial in the healthcare industry, particularly in the design and manufacture of medical devices and equipment. Precision engineering is required for the production of surgical instruments, imaging devices, and diagnostic machines. Robotic surgery systems, which enhance precision and reduce recovery times, are a notable application of mechanical technology in healthcare. Additionally, prosthetics and implants benefit from advanced materials and manufacturing techniques, improving patient outcomes and the quality of life. Construction. In the construction industry, mechanical technology is applied in the design and operation of heavy machinery, such as cranes, excavators, and bulldozers. These machines enable efficient and safe construction processes from earth moving to building assembly. Mechanical systems are also used in HVAC, heating, ventilation, and air conditioning, and plumbing systems, ensuring the functionality and comfort of buildings. Advanced construction techniques such as prefabrication and modular construction leverage mechanical technology to reduce construction time and costs. Consumer products. The production of consumer products, ranging from household appliances to electronics, relies on mechanical technology for design, manufacturing, and quality control. Automated assembly lines and precision manufacturing techniques ensure consistent product quality and efficient production. Innovations in materials and mechanical design contribute to the development of durable, energy-efficient, and user-friendly products. Agriculture. Mechanical technology has revolutionized agriculture through the development of advanced machinery and equipment. Tractors, harvesters, and irrigation systems improve the efficiency and productivity of farming operations. Precision agriculture technologies such as GPS-guided machinery and automated systems optimize planting, harvesting, and resource management, reducing waste and increasing yields. Mechanical technology continues to drive advancements across these industries, enabling innovation, improving efficiency, and supporting the development of new products and solutions. As technology evolves, its applications in modern industry are likely to expand further, contributing to economic growth and societal progress. 2. Basic concepts and terminology. There are several fundamental ideas you should know about when learning more about mechanical technology. Units and measurements. Units and measurements are fundamental aspects of mechanical technology, providing a standardized way to quantify and communicate physical quantities. Here are key units and measurement systems commonly used in mechanical technology. International System of Units, or SI. The SI system is the most widely used system of units in mechanical technology and scientific fields worldwide. It consists of 7 base units from which other units are derived. 1. Length, meter. 2. Mass, kilogram. 3. Time, second. 4. Electric current, ampere. 5. Temperature, Kelvin. 6. Amount of substance, mole. 7. Luminous intensity, candela. Derived units. Derived units are combinations of base units and are used to express other physical quantities. Some common derived units in mechanical technology include force, Newton, derived from mass and acceleration. Pressure, Pascal, derived from force and area. Energy, Joule, derived from force and distance. Power, Watt, derived from energy and time. Imperial system. While less commonly used in scientific contexts, the imperial system is still prevalent in some regions, especially in the United States. Key units include length, inch, foot, yard, mile. Mass, ounce and pound. Force, pound force. Conversion factors. Converting between different units is essential in mechanical technology, especially when working with international collaborators or utilizing data from various sources. Conversion factors are used to convert measurements from one unit to another. For example, 1 meter equals 3.28084 feet. 1 kilogram equals 2.20462 pounds. 1 Pascal equals 0.00014537 psi, or pounds per square inch. Precision and accuracy. In mechanical technology, precise measurements are crucial for ensuring the quality and reliability of products and processes. Precision refers to the consistency and repeatability of measurements, while accuracy refers to how closely the measured value aligns with the true value. Proper calibration of instruments and adherence to standardized measurement procedures are essential for achieving accurate and precise results. Instrumentation. Various instruments and devices are used in mechanical technology for measurement purposes, including calipers, used for measuring dimensions such as length, width, and thickness. Micrometers provide highly accurate measurements of small distances. Gauges, used to measure pressure, temperature, and other physical quantities. Sensors convert physical parameters such as force, displacement, and temperature into electrical signals for measurement and control purposes. In summary, units and measurements are foundational concepts in mechanical technology, facilitating communication, standardization, and the accurate characterization of physical phenomena. Understanding and applying these concepts are essential for success in the field. Force and motion. Force and motion are fundamental concepts in mechanical technology, governing the behavior and interactions of objects and systems. Force is a vector quantity representing the interaction between two objects, causing a change in their motion or deformation. It can be contact, such as friction, or long range, like gravitational forces. Newton's law of motion describes how objects behave under the influence of forces. Force is typically measured in newtons, or N, in the SI system, or pounds force, or lbf, in the imperial system. Motion refers to the change in position of an object over time, relative to a reference point. It can be linear, rotational, or projectile. Velocity and acceleration describe the rate of change of position and velocity, respectively, and are crucial for characterizing motion. In mechanical technology, force and motion have various applications. Engineers use them to design efficient and reliable machines and systems. Analysis of forces and motion helps evaluate performance and safety, optimize transportation systems, design control systems, and assess structural integrity. In vehicles, these principles are vital for optimizing performance, fuel efficiency, and safety. Understanding force and motion is essential for engineers and practitioners in mechanical technology, shaping the design, analysis, and operation of machines, systems, and structures. Energy and power. Energy and power are essential concepts in mechanical technology, shaping the design, operation, and efficiency of machines and systems. Energy represents the ability to do work or produce heat, manifesting in various forms such as kinetic, potential, thermal, chemical, and electrical energy. The unit of energy is the joule. Power, on the other hand, quantifies the rate at which work is done or energy is transferred or converted. It measures the speed at which energy is utilized or generated. Power is measured in watts, or W, with 1 watt equal to 1 joule per second. In mechanical technology, energy and power find diverse applications. They are crucial for machine operation, efficiency analysis, and the design and optimization of renewable energy systems. Thermal systems, including HVAC and refrigeration, heavily rely on energy and power principles. Similarly, electrical systems depend on power for capacity determination and energy consumption assessment. Understanding energy and power is fundamental for engineers and practitioners in mechanical technology, enabling them to enhance performance, conserve resources, and promote sustainability in various applications. 3. Materials science. Materials science is a multidisciplinary field that explores the properties, structure, design, and applications of materials. It encompasses aspects of physics, chemistry, engineering, and biology to understand and manipulate the behavior of materials at the atomic and molecular levels. Properties of materials. Properties of materials encompass a wide spectrum that governs their behavior and suitability for diverse applications. Understanding these properties is essential for material selection, design, and engineering. Here are key properties categorized. Mechanical properties. Strength, hardness, elasticity, ductility, and brittleness dictate how materials respond to applied forces, whether in tension, compression, or shear. Thermal properties. Thermal conductivity and expansion influence a material's ability to conduct heat and its dimensional stability with temperature changes. Electrical properties. Electrical conductivity and dielectric strength determine a material's ability to conduct electricity or act as an insulator. Optical properties. Transparency, reflectivity, and refractive index describe how materials interact with light, affecting their appearance and utility in optical applications. Chemical properties. Corrosion resistance and chemical stability determine a material's durability and compatibility in various environments. Other properties. Density, magnetic properties, and biocompatibility also play crucial roles in material selection and application. Understanding these properties empowers materials scientists and engineers to select or develop materials tailored to specific requirements across industries like construction, manufacturing, electronics, and medicine. Metal alloys. Metal alloys are combinations of two or more metallic elements designed to enhance specific properties or characteristics. They typically consist of a base metal and one or more alloying elements, altering properties like strength, hardness, corrosion resistance, and conductivity. Various types of metal alloys serve distinct purposes. Steel, an alloy of iron and carbon, often includes additional elements like manganese, chromium, or nickel to improve specific attributes such as strength or corrosion resistance. Stainless steel, a variant of steel, contains chromium for enhanced corrosion resistance, often with additional elements like nickel or molybdenum. Aluminum alloys blend aluminum with elements such as copper, magnesium, or silicon to boost strength, corrosion resistance, or other desired qualities. Brass, a blend of copper and zinc, is prized for its corrosion resistance and malleability, making it ideal for decorative and plumbing applications. Bronze, composed of copper and tin, sometimes with other elements like aluminum or phosphorus, offers exceptional wear resistance, suited for bearings, gears, and artistic endeavors. Metal alloys boast a wide array of properties. Strength can be engineered to suit specific applications, from structural components to aerospace materials. Hardness can be increased for enhanced wear resistance and durability. Corrosion resistance can be heightened, particularly with the addition of chromium or nickel, ensuring durability in harsh environments. Conductivity varies among alloys, with some exhibiting excellent electrical conductivity for use in electrical and electronic components. Machinability can be adjusted to ease fabrication and machining processes. Metal alloys find applications across diverse industries. They form structural components in buildings, bridges, vehicles, and infrastructure. They serve in automotive and aerospace components, electrical wiring, and electronic devices. They feature in consumer goods like appliances, utensils, and jewelry. They are vital in medical devices, implants, and industrial machinery. Metal alloys offer versatility, strength, and an array of properties that make them indispensable in modern manufacturing and engineering. Polymers and composites. Polymers and composites are two important classes of materials with diverse applicants across various industries. Here's an overview of each. Polymers. Polymers are large molecules composed of repeating subunits called monomers. They are characterized by their long chains and can be natural or synthetic. Common natural polymers include cellulose, proteins, and rubber, while synthetic polymers include plastics like polyethylene, polypropylene, and PVC. Key points about polymers include versatility. Polymers can be tailored to exhibit a wide range of properties, from flexible and lightweight to strong and rigid, making them suitable for diverse applications. Processing. Polymers can be processed using techniques such as injection molding, extrusion, and casting, allowing for mass production of complex shapes and designs. Applications. Polymers are used in various industries, including packaging, automotive, construction, healthcare, and electronics, due to their lightweight, corrosion resistance, and low cost. Composites. Composites are materials composed of two or more distinct phases, typically a matrix and reinforcement. The matrix material holds the reinforcements together and transfers loads between the reinforcement elements. Common types of composites include fiber-reinforced composites. Consist of fibers embedded in a matrix material, such as carbon fiber reinforced polymer, or CFRP, and glass fiber reinforced polymer. These composites offer high strength to weight ratios and are used in aerospace, automotive, and sporting goods. Particulate composites contain particles dispersed in a matrix material, such as metal matrix composites and ceramic matrix composites. These composites offer improved mechanical and thermal properties and find applications in high-performance engines, cutting tools, and thermal protection systems. Laminar composites consist of layers of materials bonded together, such as plywood and fiberglass reinforced composites. These composites offer tailored properties and are used in construction, marine, and automotive industries. Applications. Polymers and composites find applications across various industries. Automotive. Polymers are used in interior and exterior components, while composites are used in lightweight structures and high-performance parts. Aerospace. Composites are extensively used in aircraft components to reduce weight and improve fuel efficiency. Construction. Polymers are used in insulation, piping, and flooring, while composites are used in bridges, buildings, and wind turbine blades. Electronics. Polymers are used in cables, casings, and packaging, while composites are used in circuit boards and electronic enclosures. In summary, polymers and composites are versatile materials with unique properties that enable a wide range of applications across industries. From everyday consumer products to high-performance aerospace components. Ceramics. Ceramics are a diverse class of materials known for their inorganic, non-metallic composition, typically comprising metallic and non-metallic elements. These materials possess unique properties that set them apart. Ceramics are often exceptionally hard and resistant to wear and abrasion, making them suitable for applications requiring durability, such as cutting tools and wear-resistant coatings. They exhibit high temperature stability, able to withstand elevated temperatures without melting or deforming. This property makes ceramics ideal for use in environments such as furnaces, engines, and aerospace applications. Many ceramics are excellent electrical insulators, finding use in electronic components, insulators, and capacitors. Ceramics are often resistant to chemical corrosion and degradation, making them suitable for harsh chemical environments. However, ceramics are also inherently brittle and prone to fracture under sudden impact or stress. Despite this, advances in materials science have led to the development of tougher ceramic materials through techniques like ceramic matrix composites and nanostructuring. Ceramics encompass various types, including traditional ceramics like pottery and refractory materials, advanced ceramics like alumina and silicon carbide, and bioceramics for biomedical applications. In applications ranging from electronics and automotive to aerospace and medical fields, ceramics play crucial roles due to their unique combination of properties, making them indispensable in modern technology and industry. Part 2. Mechanics of machines. 4. Statics and dynamics. Statics and dynamics are two branches of mechanics that deal with the study of objects and systems at rest, statics, or in motion, dynamics. Equilibrium of forces. Equilibrium of forces is a fundamental concept in statics, describing a state where the net force acting on an object or system is zero. In equilibrium, forces acting in different directions balance each other out, resulting in no overall acceleration or change in motion. For an object or system to be in equilibrium, two conditions must be met. 1. Force balance. The sum of the forces in each direction, x, y, or z, must be zero. This condition ensures that there is no net force causing a linear acceleration. 2. Torque balance. The sum of the torques, or moments, about any point must be zero. Torque is the rotational equivalent of force, and torque balance ensures that there is no net tendency for rotation. There are two types of equilibrium. 1. Static equilibrium. In static equilibrium, an object or system is at rest, and all forces and torques are balanced. This state is common in structures and objects at rest on a surface. 2. Dynamic equilibrium. In dynamic equilibrium, an object or system is moving at a constant velocity, and all forces and torques are balanced. This state is less common in everyday situations, but occurs in systems with constant velocity motion, such as objects in free fall with terminal velocity. Understanding equilibrium of forces is essential in various fields, including engineering, physics, and architecture. Equilibrium principles help ensure stability, safety, and structural integrity in design and analysis processes. Kinematics of machinery. Kinematics of machinery is a branch of mechanical engineering that focuses on the study of the motion of machines and mechanisms without considering the forces that cause motion. Instead, it deals with the geometric aspects of motion, such as displacement, velocity, and acceleration. By analyzing the kinematics of machinery, engineers can determine the relationships between input and output motions in various types of mechanisms, such as linkages, gears, cams, and belts. This analysis is crucial for designing machines with desired motion characteristics, optimizing performance, and ensuring reliability. Kinematics of machinery also plays a vital role in robotics, where precise control of motion is essential for the operation of robotic arms, manipulators, and other automated systems. By studying the kinematics of robotic mechanisms, engineers can design robots capable of performing complex tasks with accuracy and efficiency. Dynamics of machinery. Dynamics of machinery is a pivotal field within mechanical engineering, delving into the forces and motions of machines and mechanical systems. In contrast to kinematics, which focuses on the geometric aspects of motion, dynamics dives into the forces and torques that drive motion and their impacts on machine components. By scrutinizing the dynamics of machinery, engineers gain insights into how various forces, such as inertia, gravity, friction, and applied loads, shape machine behavior. This analysis is essential for forecasting machine performance, stability, and safety across diverse operational scenarios. This field encompasses a broad spectrum of topics, including force analysis to pinpoint the forces and torques at play on machine elements, motion analysis to scrutinize linear and rotational motion and their velocity and acceleration profiles, vibration analysis to understand machine dynamics under external or internal sources of vibration, balancing techniques to mitigate vibration and wear on rotating components, and analysis of reciprocating machinery dynamics, essential in engines and pumps. Mastering the dynamics of machinery empowers engineers to craft machines that operate with efficiency, reliability, and safety, while minimizing issues like vibration, noise, and wear. This expertise finds application across industries such as automotive, aerospace, manufacturing, power generation, and robotics. 5. Strength of materials. Strength of materials is a branch of engineering mechanics that focuses on understanding how materials behave under various loading conditions. It explores the relationship between the external forces acting on a material and its internal response, including stress, strain, and deformation. Stress and strain. In the domain of strength of materials, stress and strain emerge as foundational concepts elucidating how materials react to external forces. Stress delineates the internal force exerted per unit area within a material when subjected to external loads. It is quantified in units like pascals or PA or pounds per square inch or PSI, and manifests in various forms, including tensile, compressive, and shear stress. Strain, conversely, quantifies the deformation experienced by a material relative to its original size under stress. Typically expressed dimensionlessly or as a percentage, strain can be categorized into tensile, compressive, and shear strain, reflecting the material's response to different stress types. The comprehension of stress and strain is pivotal in engineering design and material selection. Engineers leverage stress-strain relationships to discern material properties like elasticity, yield strength, ultimate tensile strength, and modulus of elasticity. By analyzing stress and strain behaviors, engineers optimize designs, predict material failure, and ensure the structural integrity and safety of engineering systems. Mechanical properties. Mechanical properties encompass a diverse range of characteristics crucial for understanding how materials respond to applied forces or loads. These properties are pivotal in engineering design, material selection, and structural analysis. Strength, the ability to withstand applied forces without deformation or failure, includes parameters like tensile, compressive, and shear strength. Hardness measures a material's resistance to penetration or scratching, indicating its ability to withstand localized deformation. Elasticity describes a material's capacity to deform reversibly under stress and return to its original shape when the stress is removed. It's quantified by parameters such as Young's modulus and Poisson's ratio. Ductility signifies a material's ability to deform plastically before fracturing under tensile stress, while brittleness indicates its tendency to fracture without significant plastic deformation. Toughness combines strength and ductility, representing a material's ability to absorb energy and deform plastically before fracturing, crucial in applications involving impact or shock loading. Fatigue resistance and creep resistance denote a material's ability to withstand cyclic loading or repeated stress and resist deformation or flow under constant stress or load at elevated temperatures, respectively. Comprehending these mechanical properties empowers engineers to select suitable materials, predict material behavior, and design structures or components for optimal performance, reliability, and safety. Failure theories. Failure theories are analytical models used in engineering to predict the conditions under which a material or structural component will fail. These theories provide insights into the failure mechanisms and help engineers design structures with appropriate safety margins. Here's an overview. Types of failure theories. 1. Maximum stress theory or normal stress theory. This theory predicts failure when the maximum stress in a material exceeds its ultimate strength under uniaxial loading. It assumes that failure occurs when the maximum stress reaches the material's ultimate tensile or compressive strength. 2. Maximum strain theory or normal strain theory. This theory predicts failure when the maximum strain in a material exceeds its ultimate strain under uniaxial loading. It assumes that failure occurs when the maximum strain reaches the material's ultimate tensile or compressive strain. 3. Maximum shear stress theory or Tresca criterion. This theory predicts failure when the maximum shear stress in a material exceeds its shear strength. It is based on the assumption that failure occurs when the maximum shear stress reaches the material's shear strength. 4. Maximum distortion energy theory or von Mises criterion. This theory predicts failure when the distortion energy density in a material exceeds a critical value. It accounts for both normal and shear stresses and is widely used for ductile materials. It assumes that failure occurs when the distortion energy density reaches a critical value, known as the yield strength. 5. Maximum principal stress theory, or Rankine criterion. This theory predicts failure when the maximum principal stress in a material exceeds its ultimate strength. It is applicable to brittle materials and assumes that failure occurs when the maximum principal stress reaches the material's ultimate tensile or compressive strength. Applications. Failure theories are used in various engineering disciplines, including structural engineering, mechanical engineering, aerospace engineering, and materials science. They help engineers assess the safety and reliability of structures and components, optimize designs, and prevent catastrophic failures. By employing failure theories, engineers can identify potential failure modes, determine critical loading conditions, and ensure that structures and components meet design requirements and safety standards. These theories serve as valuable tools in the design, analysis, and optimization of engineering systems across diverse industries. 6. Machine elements. Machine elements are individual components or parts of a machine that perform specific functions to enable the overall operation of the machine. These elements are typically designed to withstand various loads, transmit motion or power, and provide support or guidance within the machine assembly. Bearings and lubrication. Bearings play a crucial role in machinery by providing support, reducing friction, and facilitating smooth motion between moving parts. They come in various types, including plain bearings, ball bearings, roller bearings, and thrust bearings, each suitable for different applications and load conditions. Lubrication is essential for bearings to operate effectively, reducing friction and wear between contacting surfaces. Lubricants, such as oil or grease, are used to create a film between moving parts, preventing metal-to-metal contact and dissipating heat. Proper lubrication ensures longer bearing life, smoother operation, and reduced maintenance requirements. Gears and gear trains. Gears and gear trains are essential components in machinery, transmitting motion and power between rotating shafts, while altering speed, torque, and direction. Gears consist of toothed wheels that mesh together to transmit motion and torque. They come in various types, including spur gears, helical gears, bevel gears, and worm gears, each suited for specific applications. Gear trains are arrangements of multiple gears connected to transmit motion and power between input and output shafts. They can be classified based on their configuration and purpose, such as parallel shaft gear trains, epicyclic gear trains, and differential gear trains. Gear trains enable speed reduction, speed increase, direction reversal, and torque amplification, depending on the arrangement of gears within the train. They are widely used in machinery, automotive transmission, power transmission systems, and industrial equipment to achieve desired mechanical outcomes. Shafts and couplings. Shafts and couplings are integral components in machinery used to transmit rotary motion and torque between rotating parts. Shafts are long, cylindrical components that rotate around an axis and often serve as the backbone of a machine. They transmit power from a motor or engine to various parts of the machine, such as gears, pulleys, or wheels. Shafts must withstand torsional loads, bending moments, and other forces while maintaining dimensional stability and alignment. Couplings are mechanical devices used to connect two shafts together at their ends to transmit torque. They compensate for misalignment between shafts and absorb shocks or vibrations, preventing damage to the machinery. Couplings come in various types, including rigid couplings, flexible couplings, and fluid couplings, each suited for different applications and torque transmission requirements. Together, shafts and couplings form an essential part of machinery, enabling the transmission of motion and power while accommodating misalignment and reducing vibration for smooth and efficient operation. Fasteners and springs. Fasteners and springs are essential components in machinery and mechanical systems, each serving distinct yet crucial functions. Fasteners, such as bolts, screws, nuts, and rivets, are used to securely join components together. They provide mechanical strength and integrity to assembled structures, ensuring stability and reliability. Fasteners come in various sizes, shapes, and materials to accommodate different applications and loads. Proper selection of fasteners is critical to ensuring the structural integrity and safety of machinery and structures. Springs are mechanical devices designed to store and release mechanical energy when subjected to deformation. They are commonly used to absorb shocks, maintain tension or compression, or provide suspension and damping in machinery. Springs come in various types, including coil springs, leaf springs, torsion springs, and gas springs, each with specific characteristics suited for different applications. Springs play a crucial role in controlling motion, absorbing vibration, and providing flexibility in mechanical systems. Together, fasteners and springs contribute to the functionality, reliability, and safety of machinery and mechanical systems. Proper selection, installation, and maintenance of these components are essential for ensuring optimal performance and longevity of machinery and structures. Part 3. Thermodynamics and Heat Transfer. 7. Fundamentals of thermodynamics. The fundamentals of thermodynamics encompass the study of energy and its transformations in systems. It explores concepts such as heat, work, and the laws governing energy transfer and conversion. Thermodynamics plays a pivotal role in various fields, including engineering, physics, chemistry, and environmental science, providing a framework for understanding and analyzing energy processes and systems. Laws of thermodynamics. The laws of thermodynamics are fundamental principles that govern the behavior of energy and its transformations in systems. There are 4 laws, with the first 3 being the most commonly discussed. 1. Zeroth Law of Thermodynamics. This law establishes the concept of thermal equilibrium. It states that if 2 systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In simpler terms, it implies that temperature is a fundamental property that allows systems to be in equilibrium with each other. 2. First law of thermodynamics, or law of conservation of energy. This law states that energy cannot be created or destroyed. It can only be converted from one form to another. In other words, the total energy of an isolated system remains constant over time. Mathematically, this can be expressed as triangle U equals Q minus W, where triangle U is the change in internal energy of the system, Q is the heat added to the system, and W is the work done by the system. 3. Second law of thermodynamics. This law introduces the concept of entropy, which is a measure of the disorder or randomness in a system. It states that in any energy transfer or transformation, the total entropy of an isolated system always increases over time. This implies that processes occurring in nature tend to move towards states of higher entropy, leading to the idea of the arrow of time and the irreversibility of certain processes. 4. Third law of thermodynamics. This law states that as the temperature of a system approaches absolute zero, 0 Kelvin or minus 273.15 degrees Celsius, the entropy of the system approaches a minimum or constant value. In other words, it is impossible to reach absolute zero through any finite number of processes. This law provides insight into the behavior of systems at extremely low temperatures and is often used in the study of quantum mechanics and condensed matter physics. These laws form the foundation of thermodynamics and are essential for understanding and analyzing energy systems and processes in various scientific and engineering applications. Thermodynamic cycles. Thermodynamic cycles are sequences of thermodynamic processes that occur in a closed system to achieve a specific objective, such as converting heat into mechanical work, or vice versa. These cycles are fundamental in understanding the operation of heat engines, refrigeration systems, and other energy conversion processes. Common thermodynamic cycles include 1. Carnot cycle. The Carnot cycle is an idealized reversible thermodynamic cycle that operates between two heat reservoirs at different temperatures. It consists of 4 processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. The Carnot cycle serves as a benchmark for the maximum efficiency of heat engines. 2. Rankine cycle. The Rankine cycle is commonly used in steam power plants to generate electricity. It involves the vaporization and condensation of a working fluid, typically water, to produce mechanical work. The Rankine cycle includes processes such as heating, expansion, cooling, and compression. 3. Brayton cycle. The Brayton cycle is the basis for gas turbine engines used in aircraft propulsion and power plants. It involves the compression, combustion, expansion, and exhaust of a gas or air to produce thrust or mechanical work. The Brayton cycle operates on the principles of constant pressure and constant volume heat addition and rejection. 4. Refrigeration cycle. Refrigeration cycles are used in refrigeration and air conditioning systems to transfer heat from a low-temperature environment to a high-temperature environment. Common refrigeration cycles include the vapor compression cycle and the absorption cycle. These are just a few examples of thermodynamic cycles, each tailored to specific applications and operating conditions. Understanding thermodynamic cycles is essential for designing efficient energy conversion systems and optimizing their performance. Refrigeration and air conditioning. Refrigeration and air conditioning systems are essential for maintaining comfortable and controlled environments in various settings, including homes, offices, commercial buildings, and industrial facilities. Refrigeration systems operate on the principle of removing heat from a space or substance, thereby lowering its temperature. They consist of several key components, including a compressor, condenser, expansion valve, and evaporator. The refrigerant circulates through these components, undergoing phase changes to absorb heat from the space or substance and release it to the surrounding environment. Air conditioning systems, on the other hand, not only cool but also dehumidify and purify the air to enhance comfort and air quality. They typically consist of similar components as refrigeration systems, with the addition of air handling units and ductwork to distribute conditioned air throughout the space. Both refrigeration and air conditioning systems play critical roles in various industries, including food storage and preservation, pharmaceuticals, manufacturing, and transportation. They contribute to human comfort, health, and productivity while also facilitating the preservation of perishable goods and materials. 8. Heat transfer. Heat transfer is a fundamental process in which thermal energy is exchanged between systems or objects due to temperature differences. It plays a crucial role in various natural and engineering phenomena, influencing processes such as heating, cooling, and energy conversion. Conduction. Conduction is one of the primary modes of heat transfer, occurring when heat flows through a material or between materials in direct contact. This process relies on molecular interactions within the material. When a material is heated, its molecules gain kinetic energy and vibrate more rapidly. These vibrating molecules collide with neighboring molecules, transferring energy to them in the form of heat. This transfer continues along a gradient from regions of higher temperature to regions of lower temperature until thermal equilibrium is reached. Conduction is most effective in solids, where molecules are closely packed and can transfer energy efficiently through direct contact. Materials with high thermal conductivity, such as metals, conduct heat more effectively than materials with low thermal conductivity, such as insulators. Convection. Convection is a mode of heat transfer that occurs through the movement of fluids, liquids, or gases. It involves the transfer of heat energy from one region to another by the actual movement of the fluid itself. Convection can be classified into two types: natural convection and forced convection. 1. Natural convection. Natural convection occurs when a fluid is heated, causing it to expand and become less dense. The lighter, warmer fluid rises while the cooler, denser fluid sinks, creating a natural circulation pattern known as a convection current. This process is commonly observed in phenomena such as the rising of hot air and the circulation of water in a pot heated on a stove. 2. Forced convection. Forced convection involves the use of an external force, such as a pump or a fan, to induce fluid motion and enhance heat transfer. In forced convection, the fluid flow is driven by external factors rather than temperature differences alone. This process is widely used in applications such as HVAC systems, heat exchangers, and cooling towers. Convection is an important mechanism for transferring heat in many natural and engineering systems. It is particularly effective in fluids, where the fluid motion enhances heat transfer rates compared to conduction alone. Understanding convection is crucial for designing efficient heat transfer systems and optimizing thermal management processes in various applications. Radiation. Radiation is a mode of heat transfer that occurs through electromagnetic waves. Unlike conduction and convection, radiation does not require a medium to propagate and can transfer heat through vacuum. All objects emit thermal radiation in the form of electromagnetic waves as a result of their temperature. These waves carry energy away from the object and can be absorbed by other objects, increasing their temperature. The amount of radiation emitted by an object depends on its temperature and surface properties, such as emissivity. The rate of heat transfer by radiation is governed by the Stefan-Boltzmann law, which states that the radiant heat flux emitted by a surface is proportional to the fourth power of its absolute temperature. Additionally, the rate of heat transfer between two surfaces depends on their temperatures, areas, and their orientation relative to each other. Radiation is significant in various applications, including heating and cooling systems, solar energy collection, thermal insulation, and electronics cooling. Understanding radiation is essential for designing efficient heat transfer systems and optimizing thermal performance in engineering and scientific applications. Heat exchangers. Heat exchangers are devices designed to transfer thermal energy between two or more fluids, often of different temperatures. They play a crucial role in various industrial, commercial, and residential applications, facilitating heating, cooling, and energy recovery processes. Heat exchangers typically consist of a series of tubes, plates, or coils through which the fluids flow. These fluids can be in direct contact with each other, as in the case of direct contact heat exchangers, or separated by a barrier, as in indirect contact heat exchangers. During operation, one fluid, known as the hot fluid, transfers thermal energy to the other fluid, known as the cold fluid, as they pass through the heat exchanger. This transfer occurs due to the temperature difference between the fluids, resulting in heat exchange without mixing them together. The design and selection of heat exchangers depend on various factors, including the nature of the fluids, their flow rates, temperature ranges, pressure conditions, and the desired level of heat transfer efficiency. Common types of heat exchangers include shell and tube, plate and frame, finned tube, and double pipe heat exchangers, each suitable for different applications and operating conditions. Heat exchangers find widespread use in HVAC systems, refrigeration units, power plants, chemical processing, food and beverage industries, and many other sectors where thermal energy exchange is essential for efficient operation. They contribute to energy savings, process optimization, and environmental sustainability by facilitating the reuse and recovery of thermal energy. Part 4. Fluid Mechanics and Hydraulic Systems. 9. Fluid Mechanics Basics. Fluid mechanics is a branch of physics that deals with the study of fluids, liquids, and gases, and their behavior under various conditions. It encompasses the principles governing fluid flow, pressure, buoyancy, viscosity, and turbulence. Properties of fluids. Fluids possess several key properties crucial for understanding their behavior. Density refers to the mass per unit volume of a fluid, determining its weight per unit volume. Viscosity measures a fluid's resistance to flow, affecting its ability to deform or flow under applied force. Pressure represents the force per unit area exerted by a fluid and varies with depth in a fluid column. These properties play significant roles in various fluid mechanics phenomena, influencing fluid flow, pressure distribution, and buoyancy, among others. Understanding fluid properties is essential for analyzing fluid behavior and designing efficient systems in engineering and science. Fluid statics and dynamics. Fluid mechanics encompasses both fluid statics and fluid dynamics, each addressing distinct aspects of fluid behavior. Fluid statics deals with the study of fluids at rest or in equilibrium. It examines the forces acting on fluids and the pressure distribution within them. Key concepts in fluid statics include hydrostatic pressure, Pascal's law, Archimedes' principle, and buoyancy. Fluid dynamics, on the other hand, focuses on the study of fluids in motion. It analyzes the behavior of fluid flow, including velocity profiles, pressure gradients, and flow patterns. Key concepts in fluid dynamics include conservation of mass, conservation of momentum, Bernoulli's equation, and viscous effects. Together, fluid statics and fluid dynamics form the foundation of fluid mechanics, providing insights into the behavior of fluids in various engineering and scientific applications. Understanding these concepts is essential for designing and analyzing fluid systems, such as pipelines, pumps, turbines, and aircraft wings, among others. Flow in pipes and channels. Flow in pipes and channels is a fundamental aspect of fluid mechanics, with practical applications in various engineering disciplines, including civil, mechanical, and chemical engineering. It involves the study of how fluids move through enclosed conduits, such as pipes, ducts, and open channels. The behavior of fluid flow in pipes and channels is governed by several factors, including the type of fluid, the geometry of the conduit, and the boundary conditions. Some key concepts and phenomena associated with flow in pipes and channels include: 1. Types of flow. Flow in pipes and channels can be classified into different regimes based on the velocity and nature of the flow. These include laminar flow, turbulent flow, and transitional flow. 2. Pressure drop. The pressure drop along a pipe or channel is a critical parameter in fluid flow analysis. It depends on factors such as the flow rate, fluid properties, pipe geometry, and roughness of the conduit walls. 3. Flow resistance. Flow in pipes and channels encounters resistance due to friction between the fluid and the conduit walls. The magnitude of this resistance depends on the Reynolds number, which characterizes the flow regime as well as the roughness of the conduit walls. 4. Head losses. Head losses occur in pipes and channels due to factors such as frictional losses, sudden expansions or contractions, bends, and fittings. These losses result in a reduction in the total energy of the fluid as it moves through the conduit. 5. Flow measurement. Various techniques are used to measure flow rates in pipes and channels, including pressure, differential devices, flow meters, and velocity probes. Accurate flow measurement is essential for monitoring and controlling fluid flow in industrial and environmental systems. 6. Open channel flow. In open channels, such as rivers, streams, and canals, fluid flow is influenced by gravity, surface tension, and channel geometry. The study of open channel flow involves analyzing characteristics such as flow depth, velocity distribution, and flow resistance. Understanding the principles of flow in pipes and channels is essential for designing hydraulic systems, water distribution networks, wastewater treatment plants, and irrigation systems, among other applications. It enables engineers to optimize system performance, minimize energy losses, and ensure the efficient transport of fluids in a wide range of engineering systems. 10. Hydraulic systems. Hydraulic systems are power transmission systems that use pressurized fluids, typically oil or water, to transmit force and energy. They are widely used in various industries for performing a wide range of tasks, including lifting heavy loads, controlling machinery, and powering equipment. Hydraulic pumps and motors. Hydraulic pumps and motors are essential components of hydraulic systems, responsible for generating fluid flow and converting hydraulic energy into mechanical energy and vice versa. 1. Hydraulic pumps. Hydraulic pumps are devices that generate fluid flow by converting mechanical energy into hydraulic energy. They draw fluid from a reservoir and pressurize it to create flow, which is then directed to various components within the hydraulic system. Common types of hydraulic pumps include gear pumps, vane pumps, piston pumps, and axial piston pumps. These pumps vary in design and efficiency, allowing them to be tailored to specific applications and operating conditions. 2. Hydraulic motors. Hydraulic motors are devices that convert hydraulic energy into mechanical energy, producing rotational motion. They receive pressurized fluid from the hydraulic system and use it to drive a mechanical load, such as a conveyor belt, winch, or vehicle wheel. Hydraulic motors operate on similar principles as hydraulic pumps, but in reverse. They come in various types, including gear motors, vane motors, radial piston motors, and axial piston motors, each suited for different applications and performance requirements. Hydraulic pumps and motors play crucial roles in hydraulic systems, providing the necessary power and motion control for a wide range of industrial, mobile, and aerospace applications. Understanding the characteristics and performance of these components is essential for designing efficient hydraulic systems and optimizing their operation. Hydraulic circuit design. Hydraulic circuit design involves the creation of a system of interconnected hydraulic components that work together to perform specific tasks efficiently and reliably. Here are the key steps involved. Identify system requirements. Determine the requirements and objectives of the hydraulic system, including the desired functionality, operating conditions, flow rates, pressures, and environmental considerations. Select hydraulic components. Choose appropriate hydraulic components, including pumps, motors, actuators, such as cylinders or hydraulic motors, valves, filters, reservoirs, and hoses, based on the system requirements and performance criteria. Design system layout. Create a schematic diagram or layout of the hydraulic system, illustrating the arrangement and connections of the components. Consider factors such as component placement, fluid flow paths, accessibility for maintenance, and safety considerations. Size and specify components. Determine the size and specifications of hydraulic components, such as pumps, actuators, and valves, based on the system requirements, including flow rates, pressures, and load capacities. Ensure that the selected components can meet the performance criteria and operate within their design limits. Select control methods. Choose appropriate control methods for regulating fluid flow, pressure, and direction within the hydraulic system. This may involve the use of manual, electrical, pneumatic, or hydraulic control valves, as well as sensors, switches, and feedback mechanisms. Consider safety and reliability. Incorporate safety features and measures into the hydraulic system designed to prevent accidents, mitigate risks, and ensure reliable operation. This may include pressure relief valves, overpressure protection, emergency stop controls, and interlocks. Optimize efficiency. Design the hydraulic system to minimize energy losses, maximize efficiency, and optimize performance. Consider factors such as fluid viscosity, pressure drops, flow restrictions, and component sizing to achieve efficient operation and reduce energy consumption. Prototype and test. Build a prototype or mock-up of the hydraulic system and conduct thorough testing and evaluation to verify performance, identify any issues or deficiencies, and make necessary adjustments or improvements. Documentation and maintenance. Document the hydraulic circuit design, including schematics, specifications, component lists, and operating procedures. Establish a maintenance schedule and procedures to ensure proper upkeep, inspection, and troubleshooting of the hydraulic system over time. By following these steps, engineers can develop well-designed hydraulic circuits that meet the requirements of specific applications, provide reliable performance, and ensure safety and efficiency in operation. Applications and maintenance. Hydraulic systems find diverse applications across industries such as construction, manufacturing, agriculture, automotive, aerospace, and marine. These systems power machinery and equipment for a wide range of tasks, including lifting, pressing, bending, and material handling. Some common applications include construction equipment. Hydraulic systems drive heavy machinery like excavators, cranes, bulldozers, and loaders for earth moving, lifting, and material handling tasks at construction sites. Manufacturing machinery. Hydraulic systems are integral to machine tools, presses, injection molding machines, and other manufacturing equipment for shaping, forming, and assembling parts in industrial production processes. Agricultural machinery. Hydraulic systems power agricultural equipment such as tractors, harvesters, plows, and sprayers for planting, harvesting, and processing crops on farms. Automotive systems. Hydraulic systems are used in automotive applications, including braking systems, power steering systems, suspension systems, and transmission systems, enhancing vehicle performance, control, and safety. Aerospace and defense. Hydraulic systems play vital roles in aircraft, spacecraft, and military vehicles for controlling flight surfaces, landing gear, weapon systems, and cargo handling operations. Marine equipment. Hydraulic systems are employed in ships, boats, and offshore platforms for steering, propulsion, mooring, and cargo handling functions in marine environments. Maintenance of hydraulic systems is essential to ensure their reliable operation, longevity, and safety. Some key maintenance practices include regular inspections. Perform routine inspections of hydraulic components, including hoses, fittings, valves, cylinders, and pumps, to check for leaks, wear, corrosion, and other signs of damage. Fluid management. Monitor fluid levels, cleanliness, and condition regularly and perform fluid analysis and filtration to remove contaminants and maintain optimal fluid properties. Component lubrication. Lubricate moving parts and components as recommended by the manufacturer to reduce friction, wear, and heat generation, ensuring smooth operation and prolonging component life. Seal maintenance. Inspect and replace seals, gaskets, and O-rings as needed to prevent fluid leaks and maintain hydraulic system integrity. Pressure testing. Conduct pressure testing and performance checks periodically to verify system functionality, identify any issues or malfunctions, and make necessary adjustments or repairs. Training and education. Provide training and education to personnel responsible for operating, maintaining, and servicing hydraulic systems to ensure proper handling, troubleshooting, and repair practices. By implementing these maintenance practices, hydraulic systems can operate efficiently, minimize downtime, and extend service life, contributing to improved productivity and cost effectiveness in various industrial applications. Part 5. Electrical integration in mechanical systems. 11. Electromechanical systems. Electromechanical systems integrate electrical and mechanical components to perform specific functions, converting electrical energy into mechanical motion or vice versa. These systems are widely used in various applications across industries, including robotics, automation, transportation, manufacturing, and consumer electronics. Fundamentals of electromechanical energy conversion. Electromechanical energy conversion lies at the heart of numerous technological advancements, powering essential devices and systems across various industries. Understanding the fundamentals of this process is crucial for engineers and scientists seeking to harness electrical and mechanical energy interchangeably. At its core, electromechanical energy conversion involves the transformation of electrical energy into mechanical energy or vice versa. This process is governed by principles rooted in electromagnetism, mechanics, and energy conservation. One of the fundamental components in electromechanical energy conversion is the electric motor. Electric motors utilize the interaction between magnetic fields and electric currents to produce mechanical motion. This is achieved through the application of Ampere's law and Faraday's law of electromagnetic induction. Ampere's law states that an electric current generates a magnetic field around a conductor, while Faraday's law describes how a changing magnetic field induces an electromotive force, or EMF, in a nearby conductor. In an electric motor, a current-carrying conductor, typically a coil of wire, is placed within a magnetic field. When an electric current flows through the coil, it generates a magnetic field around the conductor. This magnetic field interacts with the external magnetic field, resulting in a mechanical force that causes the coil to rotate. This rotational motion can then be utilized to drive mechanical systems such as fans, pumps, conveyor belts, and electric vehicles. Conversely, electromechanical energy conversion also encompasses the process of generating electricity from mechanical motion, as seen in generators and alternators. These devices operate on the principle of electromagnetic induction, where a changing magnetic field induces an EMF in a nearby conductor. When a coil of wire is rotated within a magnetic field, the magnetic flux through the coil changes, inducing an EMF and generating an electric current. This current can then be harnessed to power electrical loads or stored in batteries for later use. The efficiency of electromechanical energy conversion systems depends on various factors, including the design of the components, the materials used, and the control algorithms employed. Advances in material science, electronics, and control theory have led to significant improvements in the efficiency, reliability, and performance of electromechanical systems. Electric motors and generators. Electric motors and generators are essential components in electromechanical energy conversion, serving as the driving force behind countless devices and systems in various industries. Both devices operate on the principles of electromagnetism and electromagnetic induction, albeit in opposite directions, to convert electrical energy into mechanical energy or vice versa. Electric motors are devices that convert electrical energy into mechanical energy. They consist of coils of wire known as armature windings placed within a magnetic field. When an electric current is passed through the armature windings, a magnetic field is generated around the coils, interacting with the external magnetic field to produce a mechanical force. This force causes the armature to rotate, resulting in the desired mechanical motion. Electric motors are used in a wide range of applications, from industrial machinery and appliances to automotive systems and robotics. On the other hand, generators, also known as alternators, are devices that convert mechanical energy into electrical energy. They operate based on the principle of electromagnetic induction, where a changing magnetic field induces an electromotive force in a nearby conductor. In a generator, a coil of wire is rotated within a magnetic field, causing the magnetic flux through the coil to change. This change in flux induces an electromotive force, or EMF, in the coil, generating an electric current. Generators are utilized to produce electricity in power plants, wind turbines, hydroelectric dams, and portable generators for backup power. Both electric motors and generators play critical roles in various industries and applications. Electric motors drive machinery, pumps, fans, compressors, and conveyor systems, providing the mechanical power needed for industrial processes and transportation. Generators produce electricity for residential, commercial, and industrial use, powering homes, businesses, hospitals, schools, and entire cities. The efficiency, reliability, and performance of electric motors and generators continue to improve with advancements in materials, design, and control technology, contributing to the development of more efficient and sustainable energy systems. Control systems. Control systems are fundamental to the operation of numerous technological processes and devices, providing the means to regulate, monitor, and optimize their performance. These systems are found in a wide range of applications, including industrial automation, robotics, aerospace, automotive, power generation, and HVAC, or heating, ventilation, and air conditioning. At their core, control systems consist of sensors, actuators, controllers, and feedback mechanisms that work together to maintain desired conditions or behaviors within a system. The primary objective of control system is to ensure that the system's output meets specified requirements, despite variations in input or operating conditions. There are two main types of control systems: open loop and closed loop, or feedback control systems. 1. Open loop control systems. In an open loop control system, the control action is based solely on the input signal, without considering the system's output or performance. These systems are simple and often used in applications where the system dynamics are well understood and predictable. However, they are less robust to disturbances and changes in operating conditions. 2. Closed-loop control systems. Closed-loop control systems, also known as feedback control systems, continuously monitor the system's output and adjust the control action based on feedback from sensors. This feedback loop allows the system to respond to changes in operating conditions, disturbances, and uncertainties, making closed-loop control systems more robust and accurate compared to open-loop systems. Control systems can also be classified based on their control strategy, such as proportional integral derivative control, or PID control. PID control is a widely used control strategy that adjusts the control action based on proportional, integral, and derivative terms of the error signal, or the difference between the desired set point and the actual output. PID controllers are versatile and can be tuned to achieve desired system performance. Model Predictive Control, or MPC. MPC is an advanced control strategy that utilizes dynamic models of the system to predict future behavior and optimize control actions over a specified time horizon. MPC is particularly effective in systems with complex dynamics and constraints. Adaptive control. Adaptive control systems adjust their parameters and control strategies based on changes in the system or environment, allowing for optimal performance under varying conditions. Control systems play a vital role in modern technology, enabling automation, precision control, stability, and efficiency in a wide range of applications. Advancements in control theory, sensor technology, and computing have led to increasingly sophisticated and intelligent control systems capable of meeting the demands of complex and dynamic systems. 12. Automation and robotics. Automation and robotics are revolutionizing industries across the globe, enhancing productivity, efficiency, and safety in various sectors. From manufacturing and logistics to healthcare and agriculture, automation and robotics play pivotal roles in streamlining processes, reducing costs, and improving quality. Sensors and actuators. Sensors and actuators serve as the sensory organs and muscles of automation and robotics, respectively, enabling machines to perceive and interact with their environment effectively. Sensors play a crucial role in gathering data about the surroundings, detecting physical properties such as temperature, pressure, light, proximity, and motion. They provide vital input to automation systems, facilitating real-time monitoring, detection of changes, and informed decision-making. For instance, temperature sensors monitor machinery and processes to prevent overheating, while proximity sensors detect the presence or absence of objects to trigger actions or adjust operations accordingly. Photoelectric sensors utilize light beams to identify objects, colors, or distances, aiding in precise positioning and object recognition in robotic applications. Force sensors measure forces and pressures exerted on objects or surfaces, enabling tasks such as material handling, assembly, and quality control. Motion sensors detect movement in the environment, allowing robots and automated systems to navigate, track objects, and avoid collisions. Actuators, on the other hand, are responsible for translating commands generated by automation systems into physical actions or tasks. They convert electrical, hydraulic, or pneumatic energy into mechanical motion or force, enabling machines to perform a wide range of functions. Electric motors are commonly used to produce rotational or linear mechanical motion, powering machinery, conveyors, and robotic joints. Pneumatic actuators utilize compressed air to generate fast and precise linear or rotary motion, suitable for applications such as valves, cylinders, and grippers. Hydraulic actuators harness pressurized hydraulic fluid to deliver high force output for heavy-duty tasks like construction equipment, presses, and industrial machinery. Piezoelectric actuators employ piezoelectric materials to induce mechanical deformation in response to an applied electrical voltage, enabling precise positioning and control in micro-scale applications. By integrating sensors and actuators into automation and robotics systems, engineers can create intelligent, responsive machines capable of perceiving their surroundings, making decisions, and performing complex tasks with speed, accuracy, and efficiency. Programmable logic controllers, or PLCs. Programmable logic controllers are specialized industrial computers used to automate electromechanical processes in manufacturing, assembly lines, and other industrial settings. PLCs play a vital role in controlling machinery and processes by executing programmed instructions to perform specific tasks, such as controlling motors, valves, conveyors, and robotic arms. PLCs consist of three main components: the Central Processing Unit, or CPU, input modules, and output modules. The CPU processes program instructions and communicates with input and output modules to control connected devices. Input modules receive signals from sensors and switches, converting them into digital or analog signals that the PLC can process. These signals provide information about the state of the system, such as temperature, pressure, position, or presence of objects. Output modules receive signals from the CPU and control actuators, such as motors, solenoids, valves, and relays. They convert digital or analog signals from the CPU into electrical signals that drive the connected devices, enabling the PLC to control the operation of machinery and equipment. PLCs are programmed by using specialized software, typically based on ladder logic or function block diagrams. Programmers write logic sequences that define the behavior of the system, including input conditions, logical operations, and output actions. These programs are then downloaded to the PLC's memory for execution. One of the key advantages of PLCs is their flexibility and versatility. They can be easily reprogrammed or modified to accommodate changes in the manufacturing process or production requirements. Additionally, PLCs offer robustness, reliability, and real-time operation, making them well-suited for industrial environments. PLCs have evolved over the years to incorporate advanced features such as networking capabilities, communication interfaces, and integrated diagnostics. They can communicate with other PLCs, computers, and control systems to coordinate complex processes and exchange data in real time. In summary, programmable logic controllers, or PLCs, are essential components of industrial automation systems, providing control and monitoring capabilities for a wide range of industrial processes. They enable efficient, reliable, and flexible automation solutions that improve productivity, quality, and safety in manufacturing and industrial environments. Industrial robotics. Industrial robotics refers to the use of robotic systems in manufacturing and industrial settings to automate tasks traditionally performed by humans. These robots are designed to handle a wide range of tasks, from simple repetitive actions to complex assembly and manipulation processes. Industrial robots play a vital role in increasing productivity, improving product quality, and enhancing workplace safety in various industries. There are several key components and features of industrial robotics systems. 1. Manipulator. The manipulator, or robot arm, is the most visible part of the industrial robot. It consists of a series of linked segments or joints that enable the robot to move in multiple degrees of freedom. The end effector, or tool, attached to the robot arm is used to perform specific tasks such as gripping, welding, painting, or assembly. 2. Sensors. Industrial robots are equipped with sensors to perceive their environment and provide feedback for navigation, object detection, and quality control. Common sensors used in industrial robotics include vision systems, proximity sensors, force or torque sensors, and tactile sensors. 3. Controller. The controller is the brain of the industrial robot, responsible for processing instructions, coordinating motion, and executing tasks. It communicates with sensors, actuators, and other devices to control the robot's movements and behavior. Controllers may be programmed using proprietary software or programming languages specific to the robot manufacturer. 4. End-of-arm tooling, or EOAT. End-of-arm tooling refers to the attachments or accessories mounted on the robot's end effector to perform specific tasks. EOATs can include grippers, vacuum cups, welding torches, screwdrivers, and cameras, tailored to the requirements of the application. 5. Safety systems. Industrial robots are equipped with safety features and systems to protect human operators and prevent accidents. These may include physical barriers, safety cages, emergency stop buttons, light curtains, and collaborative robot or cobot technology that allows robots to work safely alongside humans. Industrial robots are utilized in a wide range of industries, including automotive manufacturing, electronics assembly, food processing, pharmaceuticals, logistics, and aerospace. They are employed for tasks such as material handling, pick and place operations, welding, painting, inspection, packaging, and machine tending. The adoption of industrial robotics continues to grow as advancements in technology, such as artificial intelligence, machine learning, and sensor integration, enable robots to perform increasingly complex and precise tasks. Industrial robots are transforming manufacturing processes, driving efficiency improvements, reducing costs, and enabling companies to remain competitive in today's global marketplace. Automation in manufacturing. Automation in manufacturing revolutionizes production processes by integrating machinery, robotics, and computer-controlled systems to enhance efficiency and productivity. This comprehensive approach aims to reduce manual labor, enhance product quality, and lower costs. Key components include robots and robotic systems. These perform various tasks like material handling, assembly, welding, and packaging with precision and speed. Computer numerical control machining, or CNC machining. CNC machines use computer programs to control machine tools for precise and rapid part production. Automated guided vehicles, or AGVs. These mobile robots autonomously transport materials within manufacturing facilities, boosting efficiency. Conveyor systems. Conveyor belts and systems move materials, parts, and products between production stages, streamlining operations. Programmable logic controllers, or PLCs. PLCs control and automate machinery, ensuring smooth operations, safety, and monitoring performance. Vision systems and sensors. These detect, inspect, and monitor parts, products, and processes in real time for quality control and optimization. Integration and connectivity. Automation systems integrate with ERP and MES software for seamless communication, data exchange, and production planning. Benefits of automation include increased productivity, improved product quality, reduced labor costs, enhanced safety, flexibility, and lower production costs. Overall, automation transforms manufacturing, enables companies to achieve higher efficiency, innovation, and competitiveness. Part 6. Modern Technologies and Applications. 13. Advanced Manufacturing Techniques. Advanced manufacturing techniques encompass a range of cutting-edge processes and technologies designed to optimize production efficiency, enhance product quality, and enable customization in manufacturing. These techniques leverage innovative approaches and technologies to address evolving industry demands and stay competitive in the global market. Advanced robotics and automation play a crucial role in modern manufacturing, allowing for the automation of repetitive tasks, increased productivity, and improved safety. Collaborative robots, or cobots, work alongside human workers, enhancing efficiency and flexibility in production processes. Furthermore, advanced manufacturing techniques include the use of advanced materials such as composites, ceramics, and nanomaterials, which offer superior strength, durability, and performance compared to traditional materials. These materials enable the development of lightweight structures, advanced electronics, and high-performance components for various industries. Innovations in digital manufacturing technologies, such as digital twins, simulation software, and augmented reality, are also transforming the manufacturing landscape. Digital twins create virtual replicas of physical assets, allowing for real-time monitoring, optimization, and predictive maintenance of manufacturing processes. Simulation software enables engineers to simulate and analyze manufacturing processes before physical production, reducing costs and minimizing risks. CNC machining. Computer numerical control, or CNC machining, stands as a sophisticated manufacturing method employing computer-controlled machine tools to fabricate precision parts from various materials. This process operates by programming digital instructions, known as G-code, into software systems, dictating the movement and operation of cutting tools. The advantages of CNC machining are manifold. Precision and accuracy. CNC machines achieve tight tolerances and high precision, ensuring consistent quality and dimensional accuracy in manufactured parts. Flexibility. These machines are versatile, capable of producing a wide array of parts with complex geometries and intricate features, and can swiftly transition between different machining operations without extensive retooling. Efficiency. Highly automated, CNC machining reduces the need for manual intervention, increasing productivity. With continuous operation and minimal downtime, CNC machines can swiftly produce parts efficiently. Reproducibility. CNC machining guarantees uniformity and repeatability in production, enabling the consistent manufacture of identical parts with minimal variation. Cost effectiveness. Despite requiring a significant initial investment, CNC machines offer long-term cost savings through enhanced efficiency, reduced labor costs, and minimized material waste. CNC machining encompasses several processes, including milling, turning, drilling, and grinding, each tailored to different part types and materials. Milling involves material removal from a workpiece using rotating cutting tools to shape precise features. Conversely, turning rotates the workpiece while stationary cutting tools shape it into cylindrical or conical forms. Drilling creates holes in the workpiece, while grinding ensures precise surface finishing and material removal. Ultimately, CNC machining emerges as a versatile and efficient manufacturing technique, indispensable in industries such as aerospace, automotive, medical, and electronics. Its capability to fabricate intricate parts with high precision and repeatability solidifies its critical role in modern manufacturing operations. Additive manufacturing, or 3D printing. Additive manufacturing, commonly referred to as 3D printing, represents a revolutionary manufacturing technique that constructs objects layer by layer from digital designs. Unlike traditional subtractive methods that involve removing material, additive manufacturing builds up material, offering unparalleled design flexibility, rapid prototyping, and customization capabilities. In this process, a digital 3D model is generated using computer-aided design software, or CAD software, or obtained through 3D scanning. The model is then divided into thin cross-sectional layers, with each layer sequentially printed or deposited onto a build platform using various methods and materials. Additive manufacturing encompasses several techniques. Fused deposition modeling, or FDM, extrudes thermoplastic filaments through a heated nozzle, depositing material layer by layer. Stereolithography, or SLA, utilizes a vat of liquid photopolymer resin and a UV laser to selectively cure the resin, solidifying it into the desired shape. Selective laser sintering, or SLS, fuses powdered materials such as plastics, metals, or ceramics using a high-powered laser to create the final object layer by layer. Direct metal laser sintering applies the same principle as SLS, but is specifically tailored for metal powders, producing complex metal parts with high strength and durability. The advantages of additive manufacturing over traditional methods are manifold. Design freedom. Additive manufacturing allows for the creation of highly complex geometries and intricate structures that are challenging to achieve otherwise. Rapid prototyping. 3D printing facilitates rapid prototyping and iterative design processes, reducing time to market and development costs. Customization. It enables on-demand production of custom parts and products tailored to specific requirements or individual preferences. Material efficiency. Additive manufacturing minimizes material waste by using only the material needed to build the final object, thus reducing environmental impact. Manufacturing complexity. Parts with integrated features, such as internal channels, lattice structures, and lightweight designs, can be produced without assembly. Additive manufacturing finds applications across various industries, including aerospace, automotive, healthcare, and consumer goods. It is reshaping product design, manufacturing processes, and supply chains, unlocking new opportunities for innovation and efficiency. Computer-aided design, or CAD, and computer-aided manufacturing, or CAM. Computer-aided design, or CAD, and computer-aided manufacturing, or CAM, are integral components of modern manufacturing processes, facilitating the design, development, and production of complex parts and products with precision and efficiency. Computer-aided design, or CAD, involves the use of specialized software to create detailed digital models and drawings of parts, assemblies, and products. CAD software enables engineers and designers to visualize concepts, iterate designs, and simulate performance before physical prototypes are built. These digital models serve as the foundation for the entire manufacturing process, providing accurate representations of the final product's geometry, dimensions, and specifications. Computer-aided manufacturing, or CAM, complements CAD by utilizing digital models to generate instructions for machining operations and production processes. CAM software translates CAD designs into machine-readable instructions, such as G-code, which control the movements of CNC machines, 3D printers, and other manufacturing equipment. CAM software optimizes tool paths, minimizes material waste, and ensures efficient utilization of resources during production. CAD and CAM work seamlessly together to streamline the manufacturing process and improve productivity. Design optimization. CAD software allows designers to explore multiple design iterations, evaluate performance, and optimize designs for manufacturability. CAM software then translates these optimized designs into efficient manufacturing instructions, ensuring that the final product meets design specifications. Accuracy and precision. CAD software enables precise modeling of parts and assemblies, ensuring that components fit together correctly and perform as intended. CAM software translates these precise digital models into precise machining instructions, resulting in accurate and consistent production of parts. Time and cost savings. By enabling rapid prototyping, simulation, and virtual testing, CAD and CAM software reduce the time and cost associated with traditional trial and error methods. Design changes can be made quickly and easily in the digital environment, avoiding costly rework and delays in production. Integration with manufacturing processes. CAD and CAM software seamlessly integrate with CNC machines, 3D printers, and other manufacturing equipment, ensuring smooth communication and data exchange throughout the production process. This integration improves efficiency, reduces errors, and enhances overall productivity. 14. Renewable energy technologies. Renewable energy technologies harness naturally occurring and replenishable energy sources to generate electricity, heat, and fuel, offering sustainable alternatives to fossil fuels and mitigating the environmental impacts of energy production. Wind turbines. Wind turbines are a cornerstone of renewable energy generation, harnessing the kinetic energy of wind to produce electricity. These towering structures consist of several key components, including the tower, rotor blades, nacelle, and generator. 1. Tower. The tower provides structural support for the wind turbine and elevates the rotor blades to capture higher wind speeds. Tower height varies depending on site-specific wind conditions and turbine size. 2. Rotor blades. Mounted on a horizontal axis, the rotor blades capture the kinetic energy of the wind and convert it into rotational motion. Modern blades are typically made of lightweight, aerodynamic materials to maximize energy capture. 3. Nacelle. The nacelle houses the gearbox, generator, and other essential components of the turbine. It sits atop the tower and rotates to face the wind, optimizing energy production. 4. Generator. The generator converts the rotational energy from the rotor blades into electricity. Most wind turbines use electromagnetic generators, where the rotation of a magnet within a coil induces an electrical current. Wind turbines operate on the principle of aerodynamic lift, with the shape and angle of the rotor blades designed to maximize energy capture. As the wind blows, it exerts force on the blades, causing them to rotate. The rotational motion drives the generator, producing electricity that is fed into the electrical grid for distribution. Wind turbines come in various sizes and configurations, ranging from small-scale turbines for residential or agricultural use to utility-scale turbines installed in wind farms. Advances in technology have led to larger, more efficient turbines capable of harnessing energy from lower wind speeds and operating in a wider range of conditions. Wind energy offers numerous benefits, including zero greenhouse gas emissions, abundant resource availability, and energy independence. It plays a crucial role in transitioning to a sustainable energy future by reducing reliance on fossil fuels. As wind power continues to expand globally, wind turbines will play a vital role in meeting growing energy demand while minimizing environmental impact. Solar power systems. Solar power systems harness the abundant energy from sunlight to generate electricity, offering a clean and renewable alternative to fossil fuels. These systems utilize photovoltaic or PV panels, solar thermal collectors, or concentrated solar power technology to capture sunlight and convert it into usable energy. Let's explore the components and operation of solar power systems. 1. Photovoltaic panels or PV panels. PV panels consist of multiple solar cells made of semiconductor materials such as silicon. When sunlight strikes the surface of a solar cell, it excites electrons, creating an electric current. PV panels are typically arranged in arrays to maximize energy capture and output. 2. Inverter. The inverter converts the direct current, or DC, electricity generated by the PV panels into alternating current electricity suitable for use in homes, businesses, and the electrical grid. Inverters also optimize system performance and ensure safety by monitoring voltage and frequency. 3. Mounting structure. Solar panels are mounted on sturdy structures, such as rooftops, ground mounts, or solar tracking systems, to optimize sunlight exposure and panel orientation. Mounting structures are designed to withstand various weather conditions and ensure optimal performance over the system's lifespan. 4. Balance of system components. Solar power systems include additional components such as wiring, disconnect switches, circuit breakers, and monitoring systems to facilitate safe and efficient operation. These balance of system components ensure proper electrical connections, protect against electrical faults, and monitor system performance in real time. Solar power systems operate by converting sunlight into electricity through the following process. Sunlight. Solar panels absorb sunlight, which consists of photons or particles of light from the sun. Photovoltaic effect. When sunlight strikes the surface of a solar cell, it excites electrons in the semiconductor material, creating an electric current. Electricity generation. The electric current produced by the solar cells is collected by the PV panels and converted into DC electricity. Inverter conversion. The DC electricity is fed into an inverter, which converts it into AC electricity suitable for powering electrical appliances, devices, and the electrical grid. Utilization. The generated electricity can be used immediately to power homes, businesses, or other electrical loads. Excess electricity can be stored in batteries for later use or fed back into the electrical grid through net metering arrangements. Solar power systems offer numerous benefits, including reduced electricity bills, energy independence, and environmental sustainability. They produce clean, renewable energy without emitting greenhouse gases or harmful pollutants, making them an essential component of the transition to a low-carbon energy future. As technology advances and costs continue to decline, solar power systems will play an increasingly significant role in meeting global energy needs while mitigating climate change. Energy storage solutions. Energy storage solutions are pivotal in efficiently integrating renewable energy sources into the electrical grid, managing fluctuations in supply and demand, and ensuring a reliable and resilient energy supply. These solutions store excess energy generated during periods of low demand or high renewable energy output and release it when needed, helping to balance the grid, improve stability, and optimize energy use. Let's explore some common energy storage technologies. Battery storage systems. These systems store electrical energy in rechargeable batteries, typically lithium-ion, lead-acid, or flow batteries. When excess electricity is available, it is stored in the batteries for later use. Battery storage systems can be deployed at various scales, from residential and commercial installations to utility-scale projects. They provide flexibility, fast response times, and high energy density, making them suitable for a wide range of applications, including peak shaving, load leveling, and grid stabilization. Pumped hydroelectric storage. Pumped hydroelectric storage facilities use water reservoirs at different elevations to store and generate electricity. During periods of excess electricity generation, water is pumped from a lower reservoir to an upper reservoir, storing potential energy. When electricity demand is high, water is released from the upper reservoir, flowing through turbines to generate electricity. Pumped hydroelectric storage is a mature and proven technology with high efficiency and large storage capacities, making it a reliable option for grid-scale energy storage. Compressed air energy storage, or CAES. CAES systems store energy by compressing air into underground caverns or storage tanks during periods of low demand. When electricity is needed, the compressed air is released and expanded through turbines to generate electricity. CAES systems offer large storage capacities and relatively low costs, particularly when paired with existing natural gas infrastructure. However, they require suitable geological formations for underground storage and may have limited geographical applicability. Thermal energy storage. Thermal energy storage systems store energy in the form of heat or cold for later use in heating, cooling, or power generation applications. Common thermal energy storage technologies include molten salt storage, ice storage, and phase change materials. These systems can be integrated with solar thermal power plants, HVAC systems, and industrial processes to optimize energy use, reduce peak demand, and enhance system efficiency. Flywheel energy storage. Flywheel energy storage systems store energy in the form of rotational kinetic energy by spinning a flywheel at high speeds. When electricity is needed, the spinning flywheel is connected to a generator to produce electricity. Flywheel systems offer rapid response times, high power density, and long operational lifetimes, making them suitable for applications requiring short-duration energy storage and fast frequency regulation. Energy storage solutions are essential for unlocking the full potential of renewable energy sources, improving grid reliability, and accelerating the transition to a clean and sustainable energy future. As technology advances and costs continue to decline, energy storage will play an increasingly critical role in shaping the future of energy systems worldwide. 15. Maintenance and safety. Maintenance and safety are essential aspects of operating renewable energy systems, ensuring reliable performance, longevity, and the protection of personnel and assets. Maintenance involves tasks such as regular inspection, cleaning, lubrication, testing, monitoring, and component replacement to optimize system performance and identify any issues that may arise. Safety protocols are crucial to prevent hazards associated with renewable energy systems, including training personnel on safe work practices, providing appropriate personnel protective equipment, implementing lockout or tagout procedures, identifying and mitigating hazards, and developing emergency response plans. Prioritizing maintenance and safety practices helps ensure the efficient and safe operation of renewable energy systems while minimizing risks and maximizing performance. Predictive maintenance. Predictive maintenance is a proactive maintenance strategy that leverages data, analytics, and machine learning algorithms to predict equipment failures before they occur. By continuously monitoring equipment performance and analyzing data from sensors, predictive maintenance aims to identify patterns, trends, and anomalies that indicate potential issues or degradation in equipment condition. This approach allows maintenance teams to schedule maintenance activities based on actual equipment health and performance, rather than relying on fixed schedules or reactive interventions after failures occur. Predictive maintenance offers several benefits, including reduced downtime, increased equipment reliability, optimized maintenance schedules, and cost savings by minimizing unnecessary maintenance tasks and extending equipment lifespan. Condition monitoring. Condition monitoring is a proactive approach to maintenance that involves continuously monitoring the performance and health of equipment to identify potential issues or deviations from normal operating conditions. This process utilizes various sensors, instruments, and data collection techniques to measure parameters such as temperature, vibration, pressure, and fluid levels. By monitoring these parameters in real time or periodically, condition monitoring allows maintenance teams to detect early signs of equipment degradation, wear, or impending failures. Condition monitoring techniques include vibration analysis, monitoring equipment vibrations to detect abnormalities that may indicate misalignment, imbalance, bearing wear, or other mechanical issues. Thermography, using infrared cameras to measure temperature variations in equipment components, identifying hotspots that may indicate electrical faults, insulation defects, or frictional heat. Oil analysis, analyzing lubricating oil samples to detect contaminants, wear particles, or chemical changes that may indicate equipment degradation or impending failures. Ultrasonic testing, using ultrasonic sensors to detect leaks, mechanical friction, or electrical arcing in equipment components. Performance monitoring, tracking equipment performance metrics such as energy consumption, production output, and efficiency to identify deviations from expected performance levels. By monitoring equipment condition in real time or periodically, condition monitoring allows maintenance teams to identify potential issues early, schedule maintenance activities proactively, and avoid unplanned downtime or costly equipment failures. It helps optimize maintenance strategies, extend equipment lifespan, and improve overall reliability and performance of industrial assets. Safety protocols and standards. Safety protocols and standards are integral to workplace safety, providing guidelines, procedures, and best practices to mitigate risks and hazards. These protocols outline measures for identifying, assessing, and addressing potential dangers associated with specific tasks, operations, or industries. Here are some common safety protocols and standards. Occupational Safety and Health Administration, or OSHA standards. OSHA sets and enforces safety and health regulations for workplaces in the United States, covering topics such as electrical safety, machine guarding, hazardous materials handling, personal protective equipment, and ergonomics. International Organization for Standardization Standards, or ISO standards. ISO develops international standards for quality, safety, and environmental management. ISO 45001 focuses on occupational health and safety management systems, providing guidelines for effective safety management practices worldwide. National Electrical Code, or NEC. The NEC establishes standards for the safe installation, operation, and maintenance of electrical systems, addressing wiring methods, grounding, overcurrent protection, and electrical equipment safety requirements to prevent electrical hazards and accidents. Process Safety Management, or PSM. PSM encompasses standards and practices aimed at preventing catastrophic incidents in industries handling hazardous materials. It includes risk assessment, process hazard analysis, mechanical integrity, and emergency response planning. Confined space entry procedures. These protocols address hazards associated with confined spaces, outlining procedures for hazard identification, evaluation, and control, as well as requirements for safe entry, rescue, and emergency response. Lockout or tagout procedures. Lockout or tagout procedures prevent accidental energy startup during equipment maintenance by isolating energy sources, securing lockout devices, and verifying equipment isolation before work begins. Fall protection. Fall protection measures include guardrails, safety nets, personal fall arrest systems, and fall restraint systems to prevent falls and minimize injury risks when working at heights. Hazard communication. Hazard communication standards require employees to communicate chemical hazards and safety precautions to employees through labels, safety data sheets, and training programs. Adhering to safety protocols and standards promotes a safer work environment, reduces accident risks, ensures regulatory compliance, and fosters a culture of safety among employees. You have been listening to Mechanical Engineering, Handbook for Electrical Technology and Machinery. Written by Phil Gilberts. Narrated by Kevin Brooker.